Okay, take a deep breath. You know the air you just pulled into your lungs is packed with trillions and trillions of invisible particles, all zipping around like crazy? What if I told you there's a simple set of rules that explains all that chaos? Well, today, that's exactly what we're going to dive into. Let's get started. I mean, really think about it for a second. How does the smell of an amazing pizza make its way all the way across the room to you? And what's actually pushing on the inside of a balloon to keep it from collapsing? It's not magic, I promise you. It's this hidden world of particles in constant motion, and we're about to figure out exactly how it works. So the key that unlocks all these mysteries is a scientific model, and it's called the Kinetic Molecular Theory, or KMT for short. The best way to think about it is like a rulebook for how gases behave. And its main idea, it's super simple. Everything is made of tiny particles, and those particles are always moving. Now, to keep things simple, scientists came up with this idea of a perfect or ideal gas. It follows 5 basic rules. And as we walk through them, you're going to see how they build this amazing picture of how gases work in the world around us. These 5 rules, they're the foundation for everything. So first things first, let's zoom in and look at the particles themselves. What are they actually doing in there? Okay, so check this out. Imagine a game of microscopic pinball, just complete chaos. These little particles are flying in perfectly straight lines until, bam, they slam into another particle or maybe the wall of whatever container they're in. Then they just bounce off in a totally new direction. And that's rule number 1, constant random motion. Okay, so what happens when you have billions and billions of these particles all smacking into the walls of their container over and over again? Well, this is where it gets really, really cool. This right here is where pressure comes from. You know, that feeling of air pressing on your skin, or the force that keeps a car tire from going flat? That's not one single thing. It's the combined force of trillions of tiny collisions happening every single second. Each little smack is tiny, but add them all up and you get a constant, steady force. So it really just boils down to this. If you want more pressure, you need one of 2 things. You either need the particles to hit the walls more often, or you need them to hit the walls harder. Keep that idea in your head, because it's the key to what's coming next. And that brings us to maybe the most important connection in this entire theory. This is the bridge that connects that invisible world of tiny moving particles to something we can actually feel and measure every day: temperature. Let's break that down, because what is temperature really? When we talk about something being hot or cold, what are we actually measuring? You know, it's actually this simple. Temperature is just a measurement of the average energy of motion, what scientists call kinetic energy. So when something feels hot, it's literally because its particles are moving and vibrating way, way faster. And when something feels cold, their particles are just moving more slowly. That's it. Heat is just motion on a microscopic scale. And hey, for those of you who like the math, there's even a formula for it. Now, don't worry about the numbers and letters here. Just focus on that big T for temperature. It just shows us that kinetic energy is directly proportional to the absolute temperature. That means if you double the temperature, you double the average energy. It's a perfect 1-to-1 relationship. All right, let's quickly run through the other rules that make a gas ideal. Basically, we just pretend that the particles are so tiny their own volume doesn't matter, that they don't attract or push each other away, and that when they collide, it's a perfect bounce where no energy is lost. Now, these aren't perfectly true in the real world, but they make the model incredibly useful for making predictions. But you and I both know the real world is messy. It's rarely ideal. So let's take a look at how this perfect model actually stacks up against reality. This is a question scientists have to ask all the time. You know, how good is our model? Does it actually describe what's happening? Do those little simplifications we just made cause any problems down the line? And the short answer is, well, it's not perfectly ideal. Here are the 2 biggest ways reality is a little different. First, real gas particles, they do actually take up a little bit of space. And second, there are very weak forces of attraction between them, especially when they get kind of close to each other. So when can we actually trust our ideal model to work pretty well in the real world? It turns out it works best at low pressures and high temperatures. And why is that? Well, at low pressure, the particles are super far apart, so their tiny size doesn't really matter. And at high temperatures, they're moving so incredibly fast that they zip right past each other before those weak little attractions can even get a grip. All right, so you've learned the rules of the game. Now it's time to put that knowledge into practice. We've got a challenge for you, something just like you might see on an IB exam. Let's see if we can apply what we've just talked about. Here's the situation. You've got a sealed, solid box filled with helium gas. You heat it up, doubling its absolute temperature. The big question is, what happens to the pressure inside? And the real challenge here isn't just getting the right answer, it's explaining why using the rules of KMT. Go ahead and pause here for a moment and think it through. Okay, you ready? The answer is the pressure will also double. If you got that, awesome job. But now for the really crucial part, the explanation. So here's part one of the reason. We just learned that temperature is really just a measure of kinetic energy, right? So if you double the temperature, you've just doubled the average energy of all those helium atoms. And that means they are all moving, on average, a whole lot faster. And what happens when all the atoms are moving faster? Two things. First, because they're zipping around more quickly, they're going to collide with the walls of the box more often. And second, each one of those collisions is going to be more powerful. It's going to have more punch. So you've got more frequent collisions plus more forceful collisions, and that all adds up to double the pressure. And that right there is the real magic of this whole theory. We just used a simple model about the invisible world of atoms to predict a real, measurable change in our world. That's what makes the kinetic molecular theory such a powerful tool for scientists. So I'm going to leave you with one last question to chew on. If temperature is just the energy of motion, what would you call the temperature at the point where all of that molecular motion just stops? Something to think about? Thanks for joining us for this explainer.